down the. Oh. Sorry. No worries. So that we're taking the z's and the bars. So once we took before if we were taking the regular tangent space, right, we wouldn't be able to do this. But once we're taking the complexified tangent space, we have these guys because those that have that I in them, right? So now what I want to do is I want to split these into, we're going to call these the holomorphic vectors, and these the anti-holomorphic vectors. Again, like whenever there's any of this split, you want to think of like they're completely equivalent, right? It's just depending on which chicken we caught first and wrote I on it, right? But once you do that, they're the same. So it's always good to have this sort of symmetry in mind. Like there's never going to be anything different for the bars or this, or the z's. They're always going to be the same. You just have to keep track of it. So we write. I'm going to write the C in there because this is a complex vector space. We'll write T10 P Cn, and that's for this is going to be the holomorphic guy. So I'm just going to take the span C of the Z, right? So we have C1. Let me put another one there. C2, right? For all the in, right? And then similarly, we get the T 0, 1. And of the bars. For all of them, right? So you can see that this is so this originally, right? It's R2n, right? So it was a 2n real dimensional vector space. We took the 2n bases and we took the complex span. So now we have this guy is a 2n dimensional complex space, right? But it's it might feel a little weird that we have something that has more dimensions, right, than the original space. So now if we do this, we have this is a n-dimensional vector space, but this is also an n-dimensional vector space, and it just depends: are you looking at the z's or are you looking at the z bars, right? So if you're doing just complex geometry, if you have nothing real, then often like people will work with this vector space only. And you really just need this vector space, and then all of the stuff that you saw in the foliation setup, right? You could just think of this and everything being holomorphic, and all of that will work, right? And then you just be using that, and everything, all the dimensions would just work correctly there. But if we're doing CR geometry, we need to worry about both of them, right? Because there's going to be that we need to worry about the interaction between the real and the complex. So, and if we write this, then obviously we get because this is the span of all of these, right? So if we get the complex tangent space, then it's just a 1, 0 sum the 0, 1. Right? So here, this works well, right? But now, what if we do like if we take a hypersurface, right? So let's maybe what I mean by hypersurface. So we want to a codimension 1 manifold, and I'll always think of the defining function, right? So we have an M, and it's a real hypersurface. So I'm really thinking of it's some subset of Cn, but really I'm just thinking of it as R2n in this case, and it's the M is you can think of it as could be just a little piece, right? It doesn't have to be closed in Cn, right? Just a submanifold. But this is this is the set of points, and I'll just write it maybe a little sloppily, where some r is 0, where r is C infinity in a neighborhood of M, and dr is not equal to 0. Right? So not equal to 0. You can just take M, but you could just say once it's on M, it's infinite, it's the neighborhood of it, right? So you could just take that neighborhood to be small enough. So it's not equal to 0 in the entire neighborhood, right? And now, how do we define, of course, the tangent space? You could just say, well, it's the x. I mean, just instead of writing it down in the x's and the x's and the y's, but if I think of capital X now at a point P, this as a tangent vector, right? So originally it's just some vector, some real tangent vector in Cn is in the tangent space of n. Maybe if it kills R, right? If you're moving along, and of course the picture is right. You have a manifold. This vector is in the tangent space. If I'm moving along, the 0 set should be, I should get 0. Like there's no derivative, right? So that, if we think of that, that allows us to define the complexified tangent space. Because if you think about it, like how are we applying this, right? If I have vector, so now let's not make it in the real vector space. Let's take it in the complexified vector space. So that's going to be. What does that mean? Well, that means it's something of the form. Do want to confuse myself first? All right. So it's AK plus AK. Something of this form. Well, bar, yeah. Sorry. Right. Where the AKs and the BKs are just complex numbers, right? We're at a fixed point, right? So we can easily just apply this to R, right? We're just taking these derivatives, right? You could write this in terms of the x's and the y's if you want to, right? Of course, we don't want to, right? We don't write it in terms of the z's and the z bars. So you have that x p is in the complexified tangent space of M. If well, again, xp applied to R, right? I differentiate along xp, I get 0. Right? It's the same thing, right? And you could also, so you can either write it like this, or you could take this space and complexify it. Take some basis, right, and complexify it, and it's the same idea, right? Because again, you're just taking a span of vectors that do this, right? So take some basis, take a complex span, right? Now we want to decompose this one. Well, we want to decompose it into things that don't have any B's and things that don't have any A's, right? Unfortunately, we're gonna be stuck. There's gonna be some things that aren't quite like that. Now, the easiest way to do it is to just define it like this. So you have P10. Well, I could just take this space and intersect it, write down the definition, intersecting this part, right? It's really what I'm doing. write down the complicated definition about it. So it's a complexified tangent space of n intersecting the complexified, with the T10 already complex. Not yeah. Right, and I can do the same thing with the T01. Right? Again, everything is always symmetric here, so nothing should be different for the bars than for the non-bars. All right. Nice. At this point, it's not quite clear exactly what this is, right? Is it even non-empty, right? Yeah, it should be the question. I mean, are there any any vectors in this intersection? Right? Maybe you always need some A's and some B's, right? But it turns out that for a hypersurface, we'll always get a very nice decompositional, maybe not as nice as this, but almost as nice. So we cannot get this, right? Because as I was saying, everything is symmetric. You will get that these spaces are always of the same dimensions. Just like they're of the same dimension here, they have to be of the same dimension here, right? Because I mean, if I bar, I get to the other one, right? So I can't bar and get something of a different dimension, right? So that means that this has even dimension. This is even dimension. However, this thing, I mean, what is this? If you think about what this is, right? I mean, it's just a single linear equation, right? So I have it's basically a kernel of linear map into R or C, right? So I'm getting and a non-zero, because right, that linear function is not zero, right? So I am getting an n-1 dimension of 2n-1, right? 2n-1 dimensional vector space. 2n-1 is odd, right? So there's no way I can write this plus this. That's even dimensional. I can't get an odd dimensional space, right? So there has to be something extra. Okay, so if I write down the tangent space of the complexified tangent space of M, well, I mean these guys are in there, right? So I mean I can always write it, and they are going to be disjoint, right? So this is going to be an orthogonal decomposition. But there has to be something else. There has to be something else. Let's call it BP. I don't think there is actually a standard letter or notation for this. Right? But people call it sometimes the bad direction. It's maybe not the best naming because it's a good direction. It's the direction that we want to focus on, right? But maybe you think of it as the bad direction. It's like this, and something goes wrong, right? And it goes wrong in that direction, right? And I'm always saying direction, right? So for hypersurfaces, that's actually one dimensional. It's always one dimensional. For hypersurfaces, once we go and I'll say what happens for higher codimension, and we'll get then it's then it can be whatever whatever dimension. But for hypersurfaces, for real hypersurfaces, this will always be one dimensional. And you can think of it, and that's a useful way of thinking of it, because we have this decomposition. We just, I mean, basically, in the decomposition, it's whatever's left over, right? But the useful way of thinking of about it is by thinking of it as a, maybe this should be not quite equal to, but it's isomorphic to. If I take the full tangent space and I mod out, basically sort of throw away all the things that are purely in C and purely in C bar, So that's a useful way of thinking of what that space is. Right. Yeah. Yeah, these could be empty. These might be. So we'll see. We'll see more. You know, basically, yeah, they're always going to have the same dimension. They're always going to have this even dimension. But like, let's say for an even dimensional manifold, I mean, maybe everything is in here. Maybe everything is in here. Maybe some sort of combination. Yeah, you know, it's. I mean, it's basically here for hypersurfaces. It has to be one basically for dimensional reasons. I just have to. So the only restriction is how are you able to split this up, right? If you think about like what's the possibility of these intersections, happening just by inclusion-exclusion principle, basically, kind of reasoning, you get that the dimensions are kind of like the possible dimensions are kind of given, and the only possible dimension for hypersurface is that this is n minus one dimensional, this is n minus one dimensional, and this is one dimensional.
So here we are seeing as a complex vector space or real vector space?
So these are all complex vector spaces, right? So the only, I think there is nothing real on this thing.
But VP can have one dimension.
Is one complex dimension. So everything is complex here, right? I mean, you can think of, there's another way of getting at this by trying to do this decomposition before complexifying. And sometimes, sometimes that's the way that people think of it. And it's, in some sense, it's easier, in some sense, it's harder. And it's maybe a little bit less natural in a sense. But what you could do is you could take, you could go here where you have just the real tangent space, and then you could think, well, what does the complex structure do to this vector space? Right? Basically, what does multiplication by I, which is a nice map, right? You take the derivative, it does something to the tangent space, right? And multiplication by I can take a tangent vector and make it not be a tangent vector, right? So that so we might kind of want to avoid that. That would be giving it a bad direction, right? And so the way that you could get at it from a real perspective is you could take multiplication by I, treat it just like a real map, take a real derivative of it, and take this guy, intersect it with this guy under the multiplication by I. So you'll get the part of the space that's invariant under multiplication by I, which is confusingly called the complex tangent space, even though it's a real tangent space. And then even more confusingly, then people put a complex structure on it, which is completely unnatural, because you can put the complex structure or the bar of it. It's you don't quite know which one is the natural one.
What are you calling it? The complexified tangent space, or no, you're not calling it anything?
This is the complexified tangent space.
Fine,
the other one is the complex tangent
yeah,
space. And the complex tangent space is a real tangent or real space, right? So, but that's why I think like this is a little bit more natural, and it's also have more natural terminology. So these are the holomorphic vectors and anti-holomorphic vectors. So does that sort of answer the question? Yeah.
Just a counter point. I've done that all my life and continue to do that. So it's perfectly natural to say.
No, it's so the non-natural part of it is giving it the complex structure. Exactly, right? Because then there's choices, right? You can either give it the Z structure or Z bar structure, right? And if that's the part, because you're basically like either projecting, I guess what you can think of it as projecting this guy onto it or this guy onto it, right?
So it's an exciting use. So if you use that direction without complexity, right? So what you actually get is actual tangent vectors, right?
Right.
So if you're on the boundary of a domain, the back direction will exactly be the I of the normal, right? And that is oftentimes quite useful.
Right. Yeah. So it's and you can also go backwards, right? You can take this thing and yeah, or intersect it with the real tangent, right? I mean, this contains the real tangent space, right? So you'll have the real tangent space on it, right? You know, the when you intersect, this decomposition doesn't survive. That's that's sort of the problem. But you can't decompose it then because yeah, I mean, those guys aren't. Right.
But you do always get something.
But you do always get like a one-dimensional guy here, right? So if you intersect, if you take this intersect with just DPM, you get the so-called complex tangent space, which is a real tangent space over here, and some bad direction, which is an actual real honest direction. Whereas here, it's still an honest complex direction. So, all right. Afterwards. Oh, right. So I want to do, let's do an example, and let's do the sort of the standard, since we're you know, Levi-flat. So let's give the standard Levi-flat example. And so this would be when you have, it's a generalization of the real line in C, right? So you have a real line in one of the variables, right? And for this, it's more convenient, instead of using C1 through Cn, I'm going to write C1 to Cn minus 1, and then I'm going to have a W. So I'm going to write this as so Z is going to be in Cn minus 1, and W is going to be in C. That's for hypersurfaces. For higher codimension, you would you know, this would be have the dimension of whatever the codimension is. So that's just naming. It makes things simpler, and you'll see why we're doing this actually, right? Because this is going to be thinking of the bad direction, right? And let's suppose that my hypersurface is given by the imaginary of W. Right? So it really is. If there were no Z's, you realize, right? There's also like there's a sort of two classes of people in CR geometry. One which will write imaginary W, one which will write real W. Right? John D'Angelo always writes real W, and like to tease him about it, like he's convinced that that's the correct way of writing. But I'm thinking, you know, imaginary W sort of makes more sense, because usually, like when you're doing when you're using implicit function term, you're usually solving for the last components, right? So this is the last component. If you're thinking of it as x1, y1, x2, y2, and so on, like the last one is the yn, right? Or whatever the real, or the imaginary part here is, right? Okay. Don't worry about it too much. So this is my my manifold, right? So that's my R. This is my R, right? So, and let's just look at the tangent spaces at 0. They're actually the same everywhere. But let's look at what happens here, right? So if you think about it, so what is this thing? Well, it's these sort of vectors. So the vectors without this guy, right, that still kill R, right? What is the measure of W, right? I can write this as W minus W bar over 2i. The 2i is kind of irrelevant, but W minus W bar, right? It's clear that if I differentiate with value of the z's, or z bar actually, there's a skill system. There's no z's, no z bars, right? So what we get, and if I have any W, then W or W bar. If I hit this guy with that, yeah, I'm going to get here with 1 over 2i or minus 1 over 2i. I get some constant, so I don't get 0. So just by sort of basic linear algebra, you get that T0 on 0 of this n is the span, also writing the C on this, the complex span of the T1, n minus 1 and 0, right? And you get the same thing for the t 0, 1. Or all right, so now what's left over, right? There's still one more, right? I mean, this the complexity tangent space of n is something 2 and 1 dimensional, right? Like it is because, right? It's, I already claimed it before, right? So we already have n minus 1 dimensional guy, n minus 1 dimensional guy. We need one more. So you need to figure out what is what is this thing, and so it's going to be a span of a single vector field. If you think about it, well, this is it's the real line, right, in the w direction. So now we're just in the w direction. Ignore the z's, right? And so it's the real direction that's going to be tangent, and the imaginary direction is going to be the normal. Let's see what I was pointing out. Exactly that. Right? And you can see that if I have the real direction, so let's just write it here, and I'll write it like this. Basically, span of the last xn, right? I'll just write it as this. The real part of w, right? If you take that vector, right? If you hit it with a multiplication by I, you get precisely the imaginary direction, right? Now this guy, you cannot write it as just in terms of the z's and the w's, right? I mean, you have to have some sort of a combination, right? Because we're taking a span, right? You can sort of ignore these halves, and in this case a half, and it's just a span of if I want w, I have to have right. And you can see, I mean, this does kill this span, right? I have to have a plus, right? So it again, you can just ignore this, right? So the w minus w bar, and so I'll get 1, then I'll get minus 1, I get 0. And if I took the imaginary w, then I would, right? I would get 2, right? For 2 over 2i. I really hit this thing in there, right? I got 1 over I. All right. Now this is really what's happening there, right? Except we're doing sort of a special case, but well, I mean, this is hyperplane, right? And we're talking about just the first derivative. All you need to know is the tangent hyperplane. So if you understand this on the tangent hyperplane, if you understand the tangent space of the tangent hyperplane, yeah, I mean that's what it is, right? So in general, this still holds. Basically the same exact thing, right? Like we cannot take every m to be equal to this, but if m is CMA, we know that we're talking about a real hypersurface.
First do the span over C, last is for span over R.
No. They're all spans over C. Everything is going to be now spans over C. We're not doing any real things.
The dimension of difference is supposed to be 1.
Yeah, it's one complex. Everything is a complex vector space. So there's no real vector space now. Right? So it's still C. Right? So I have one vector, and I'm just multiplying it by a random complex number. Does that make sense? You could, if you want to take the real version of that direction, you would take the real span over here, right? But the complex span. So maybe you're confused about like, well, if I multiply it by I, why don't I get well, because we're in the complexified version. So the complexified tangent vectors aren't really arrows. So if I take the real direction, and I think of I now, it's a different I. Now it's acting on the complexified tangent space. It's not I as a real map, right? So before I took I as a real map from Cn to Cn, I ignored the fact that it was complex. Basically, it was just
del by del x minus I del by del y. That I over there is not pushing the del by del y.
Right.
Del by.
Right.
When you write
Like
it's
a different. Yeah.
the I over there, it's not the action, the multiplication of del by del by. Otherwise, that would just become del by del.
Right.
It's just a scalar I.
Right. It's basically, the other multiplication by I is that we go all the way somewhere back over here, right? And we think of it as just a real, like we drop the complex structure, we ignore the fact that it was multiplication by I, right? And then it acts on the real vector space. But here, the I is coming from this span, I'm taking, it's coming from here, right? Not from the space. It is a little bit like you have to figure out how to.
So just to add to Louis' point, there are two I multiplications, right? One is happening in Cn, the other is the push forward of that action in the tangent space.
Right.
I
So
would
that's
say one is happening on R2N.
No, but I'm not even going to come. I'm saying one is happening at the manifold level.
Right.
Happening at the tangent space level.
Right.
No,
It's
but
the
one is
complexified
happening-
tangent space.
No,
Okay,
one
yes,
is
you're
happening
right.
at the tangent space level and the other is happening at the complexified tangent space.
Right. Because the thing that's happening on the manifold, like you can just take a derivative of it, but you're taking the real derivative of it, and then it's acting on the real tangent space. But it's not multiplied. It's still going to be the image of. So maybe let me write that down.
X goes to X, Y goes to Y minus X, right?
So,
The push forward of that is the J map, right?
And
Because
this
push
is
forward
the
is the
G.
complex.
but the J map is a real map. That's right.
And then
Right.
you complex with the J map.
Right. But then there's a different I. So let me so if I'm thinking of C, let's just say C and I have X, Y, right? If I think of the I multiplication on here, so what does it do? Like it takes X to
Y minus
Minus Y comma X.
like maybe let me call it IJ or whatever. Maybe I the real one. J is usually the map from the tangent space. I'll just do X, Y. So it's Y minus X.
Minus Y comma X.
Minus Y comma X. Okay.
This is your head, whichever head you're choosing.
Yeah. Right, going this way. Right. So it's a you have to think about like it's supposed to be the counterclockwise to rotation, right? So now this is there is no multiplication by I here, right? It was the multiplication by I here, but I forgot about the complex structure. I'm just thinking of it as a real map, right? And I took so that's the map that would take this thing, the d by d, to measure it up. But multiplying this in the complexified space by I is just I times this. It's so I times by d not equal to d by d. Right? Does that make sense?
It's multiplication 7 or something. It's a new set of scalars you
Right. And that's why we're actually getting that's why we're getting that thing to be 2n dimensional.
So there you are,
Right.
there in your example, you're going to C2, technically you're doubling the dimension, right? When you
Right.
add the scalar.
Yeah. So you could think of it also that way, right? First you go from R2 to R2, and then you say, well, if we complexify, it's really we're going into C2, right? Does that make sense? And in that C2, it's no longer a multiplication by I, right? It's an actual nice complex linear map, right? That it is like it takes a little bit of working through some examples to sort of get this straight, but yeah.
Here, one thing that I have to know, when you are acting on this R,
Yeah.
this B the next on R, so then we are seeing as a real action, right?
If this thing, well, I mean, over here, like once the way I define the BB is a complex vector space, right? So it's not the real span of this; it's a complex vector space. So you could take, I guess that would be the real BB, which would be the real span of this.
not working with del real of W, right? We're not working with that.
No, we are working with this. Yes, that's fine. I mean, you know, I mean, the complexification is just you take you can do it by just taking any basis and just taking the complex span of it, right? So it's still, I mean, you know, all of these complex spaces are still spanned by the d by dx's, d by dy's. It's just a different basis, right? It's also the span of this. I mean, just change of basis, right? It's the difference is that these guys cannot give you the real vector space because you know there's an I in there, right? So they're not, they don't even make sense. They're not in that space, so that they can't give you a basis. Does it make sense? So, right.
So one question is like, in fact, on this study, this T01M, which is the anti-holomorphic
Right.
tangent space. This is the like a CR structure of the manifold.
Right. Yes. Sometimes it's called the CR structure. Yeah. I mean, the CR. It depends on what you know what people call the CR structure. You know, it's but somehow this decomposition is the CR structure, and some people will call this this distribution, right? So we have the distribution. Yeah. That's a distribution of. I mean, it's a complexified distribution. So. But it's still the same thing. I mean, you know, we're just talking about you know, doing either linear algebra over R or linear algebra over C.
I mean, in the abstract setup, of course, like this one is evolutive submodule of the complexified mechanism. So in that sense, if you try the abstract CR structure for L, then L is actually this one. Because
right, but so the thing about so we'll get to the evolutivity because that becomes a little trickier, right? So if you take a vector in here and you take the vector field in here and you take the commutator with a vector field in here, you're fine. You get back into this space. But if you take a vector field in here and a commutator with a vector field in here, okay, suddenly it might not be in any of these spaces actually. And actually, that's basically the thing that will make something Levi-flat is if it is like. It might not be, I guess, in one of these spaces, but it's going to be, it's not going to have any component in here, right? And the whole thing about CR geometry is really measuring how much, if I take, or one way of thinking about CR geometry is, if I take a vector in here and a vector field in here, if I take a commutator, you know, how much of my commutator is in here, right? Does that, so like how much it is not a complex structure, right? It's essentially the idea. It's for like if I had a complex manifold, we'll see an example in a bit. Then the complex manifold, well, the complex manifold is too real. Yeah, there's no BP, right? And so then it's automatically, you know, back in the sum of these, and we're fine. so it's somehow because we have a BP, we might get some of these commutators being in here, and that gives us some non-flatness, basically. In a random hypersurface, that's what's going to happen, right? But yeah, these guys are going to be involutive, but this guy might not, right? So all right. So if you have a real hypersurface, we could always I could always translate it and think of it as being at zero. So maybe I'll write this after the affine. Maybe I should say complex affine. We don't want to change the complex structure, right? So if we're doing any change of the variables, we want to do holomorphic change of variables. So complex affine change. I can basically so I can translate everything to the origin, right? So I can whatever point I'm thinking of can be zero, right? Sometimes people say, you know, there exists holomorphic coordinates vanishing at zero, right? But if you think of the z's and the w's not as the coordinates, well, not as you know, elements of Cn, but functions, right? But you then work in those coordinates, and then there are elements of Cn. I can always assume that 0 is in n, and near 0 and is given by, and basically we do this, but of course, now we apply the implicit function theorem, so we're going to get something on the right hand side. This m is given by, and I'll write it maybe a little weirdly, the measure of w equals some t. Normally you get the real and imaginary parts, but I can just write those for the z's. I'll write them as t and z bars, and then the real. So it's maybe mixing up the ZZ bar notation and the real and imaginary notation, but that's really the reason why when doing this it's useful to give different names to the Z's and the W's, right? So that you have write these things in the Z's because you can essentially because we'll be able to do really just think of these as Z's and Z bars and never have to think about real and imaginary, and the W we have to specify. Right? So this is just the implicit function term. We can write it like this. Right? And now if we compute sure, oh, one more thing that I forgot. T phi at 0, 0, right? And phi at 0 is 0. Right? So it's a order 2, right? That's important. What I'm going to write next, right? So you solve, but you also rotate to make sure that tangent space is that guy, right? The real tangent space I can think of as the real tangent space I'm thinking of it as that R2n, right? Well, then maybe I don't even have to write it down. And say on chart, it's pretty much the same thing, right? At 0, right? Of course, at other points time it's going to be different, right? But at 0, right? I mean, these guys only look at the tangent space, right? So yeah, we get the same idea. So basically, what just by this sort of using the implicit function term and using a little bit of linear algebra, you see it. It's always these guys are n-1 dimensional complex n-1 dimensional spaces. This is a complex 1 dimensional space, right? For hypersurface, right? So we always have those coordinates, and really when you're working locally, you're always trying to work in some coordinates where you have this. We'll see that we can actually do a little bit of normalization over here. You can't always get rid of everything on the right hand side. That's actually the whole point of CR geometry. If you could get rid of everything over here and get that, just like what's the point, right? So this is a little bit of different than studying, let's say, manifolds, because just if you're studying real manifolds and just the differential structure, then you can always make some, you can always change variables to make it the flat hyperplane locally, right? So manifolds just by themselves are uninteresting locally, right? CR manifolds, if I think of everything's smooth now, right? So I can write down the Taylor series over here. There's actually, and this is the Chern-Moser theory, is you can normalize, you can put this into a normal form where you're slowly getting rid of basically you're zeroing out certain all the different derivatives at 0 of all different orders, but certain ones you cannot zero out. You can normalize anyway, but you cannot zero all of them out. And there's actually infinitely many that you cannot zero out. So it's by holomorphism, by holomorphic change of coordinates. So holomorphic function there's a holomorphic inverse, right? And that's really CR geometry is studying those invariants. So we'll basically look at the lowest order invariants. So there's already something in the quadratic part that you cannot get rid of. You can normalize by quite a bit. There's basically, we can normalize it. We'll get a Hermitian form in n-1 variables, and it's really the signature of that Hermitian form that is the that is the thing that you cannot get rid of, right? And you can swap the positives and negatives by taking minus something, but other than that, it's you cannot get rid of it. If you have a positive eigenvalue in the Hermitian quadratic indices, then it will stay positive. Like it might become a negative, you can swap it by negating things, but other than that, you cannot do it. So
if the expression is it dphi not equal to 0 or equal to 0?
No, it's equal to 0. So I have
No linear terms.
yeah, there's no linear terms. There's no constant terms, there's no linear terms. It's only quadratic terms and higher. So you can always do that by rotation, right? So that's just you don't need a different because rotation is just even though it's complex rotation, but you have a unitary, right? And unitary can take maybe I should say this. Complex analysts often say like a unitary is rotation. Not quite the right terminology, but yeah. So by a unitary, right? By a complex, you don't have to do a unitary doesn't change length, right? So you don't even have to change length. But here we're not even worried about that. So you can definitely rotate things, and a unitary will take any real subspace to any other real subspace, right? So you can take whatever the tangent space is, you can take it into that space, right? Does it make sense? So you can always make sure that, but that's where it ends, right? You can get rid of this is just by translation, this is by rotation, and the quadratic terms we cannot get rid of by something that's holomorphic. So, now maybe this is a good time to take a little go on a tangent basically to make a fun, which is the thing is that so here I'm thinking of if we're writing things like this, we have a very specific defining function, but if I'm going to be looking at different points, it's so this is great for looking at what happens at 0, right? Well, once you're not at 0, then things become complicated, right? You get right. Starting to get derivatives out of this, right? This has no derivatives at 0, but outside of 0 is going to have derivatives. So a lot of times this stops being useful. You want to think of what if I have just something is just given by some defining function. This is a good exercise, and I'll give you a hint of how to exercise for the discussion section, right? So if let's just do it at 0. So of course at any point. If so this is in say in Rn. This is just a real thing, right? So of course in R2n as well, right? So in Rn, if R is smooth near 0, and R0 is 0, and BR0 is non-zero, right? So that this is a defining function of some, and this should be, let's just do it for. Here's a similar thing for. So it's in some U in Rn. Just let's ignore about hypersurfaces, right? And S is another, or maybe let me just write it like this. and say G is a function, smooth function that vanishes on the zero set of R, right? Then there exists let's call it H, let's say, such that R is so H should say smooth. So that's right. Smooth H such that G is H times R.
Gradient of G not equal to
Uh,
gradient of G, D of G.
well, I mean, you can, you don't have to. If the gradient of G is not zero, then you're going to have that H is not zero. But you can just take this. This will work for any function. I mean, the place that we're really interested in is to try to do it for another defining function. So then, if so maybe I'll write it as part A, as part B, as if maybe the easier one. If dg x0 is not zero, then h is zero is not zero. Right? So you could have it will work for any smooth function that vanishes on there. Right? I mean, clearly, if it's of this form, then it vanishes on the zero set of R. Right? So the point is that there's always this division happening. And you don't, in some sense, if you think of it in the right way, you don't really need this thing. You need something else, and we'll get to that when we get to varieties. When we get to singular hypersurfaces. But this thing is basically telling you that this is a defining function for this set for a hypersurface. And so the reason for this is this will let us basically look at these tangent spaces at any point, and you don't have to worry about which defining function you're looking at, because if R and G are defining functions, and this is this is non-zero, so it's not going to be zero in a neighborhood too. It's just gonna everything is gonna work out correctly. You might get things that are multiplied by something non-zero, but other than that, if you're just looking at the spaces, everything's going to work out. So it might be certain things you might have to things that you get by multiplying by something, might even get some derivatives, but everything's going to translate correctly, right? So, for example, all those spaces, the definition of all those spaces is maybe it doesn't really matter which defining function I take, right? So, and there's maybe it's good to have a because it's the way to prove it is, if you think about it, it's actually, I don't know if how many of you have seen this, but there's a bit of a trick that a bit of a calculus trick that you want to use. So it's basically this lemma. You want to prove it using this lemma. So it's if so let's say let's call it R. R, and now let's just suppose it's just on some interval around 0. It's C infinity, and R at 0 is 0. And now I don't really have to. Maybe calling it R is actually might be confusing. Let's call it F, because it's not that R. The R is going to be a different one, so let's call it F. Right. So it doesn't really have much to do with any of this. And F is 0, then there exists C infinity. I don't know. I could make it H. That's fine. That's not going to confuse anything. C infinity H, such that that F is X times H. I can divide out, and this h is also in here, right? The smooth on here. It's not really a problem outside of 0, right? The smooth outside. The division is fine outside of 0. It's really, showing that that you can divide at 0, right? And it's sort of, it seems like you should be, right? If it's real analytic, if it's just a power series, right? It's clear that you can, right? The point is for smooth functions. For smooth functions, you have to do a little trick, and so the trick is to think of. I'll just write out half of the proof and fill in the rest of the proof. And so it is kind of like you have to do something stupid to get the smart thing out, right? So because we have everything is smooth, we can write f at any x. I'll write it as the integral from 0 to x of f prime. Right? And what you want to do is you want to do the right change of variables, right substitution to get an x out. Right? That's the, and then you have to figure out like how to apply this lemma, right? This thing, right? How to apply it to prove this, right? And the point is that this x is the defining function, right? That's the thing. But that's the main idea. All right. So it doesn't really matter, which defining function you're taking, as long as you're taking some defining function, right? As long as the derivative is not 0, everything's just gonna give you the same spaces. All right. Because the reason why I wanted to do this is because everything that we do seems to depend on the defining function, and this says no, it doesn't, right? Well, certain things like some scaling things do, but the spaces themselves don't. All right. So okay. So suppose R is a defining function. For n, right? Let's say near, there's a bit of there, 0 or not. Near some point B. We're back in Tn, right? Now we want to look at the quadratic base of this, right? So we want to look at the quadratic part of the quadratic derivatives of R, right? So, so you look at the Hessian, right? I'm going to write the Hessian in a strange way. I'm still going to call it the real Hessian, even though it's now acting on the complexified tangent spaces, right? It's still a quadratic form, but now on the complexified tangent spaces. But it's again just a change of variables, right? I mean, if you have a symmetric form on a real vector space, if you complexify, you get a Hermitian form. And if I change variables, it's better. So I'm going to change variables to use a different basis. I'm going to use the basis of the C bars, Z's and Z bars, right? And the real Hessian of R is I'm maybe not going to write the off P in here, but everything is of course evaluated at P. But I'm going to write maybe I'll write it off, evaluating at P afterwards, because there's a lot of derivatives now. So it's the second derivative R. I'm gonna start with the Z bars here and Z's here, and I'm gonna take to make sure I'm definitely doing this correctly. Because there's different ways of writing it, but I'm gonna take all the Z bar derivatives in the first component. So now, I have because we're not in that special setting, I'm thinking of Z as in Cn, right? So I have D and bar D1, right? And I have this matrix here, right? But hopefully I don't have to go to the next board. And here I'm moving these Z, so it's still Z1 bar and then Dn, right? And if I do this, then I'm going to end up at Z bar N. And now I'm going to repeat the process, 3 other times. Maybe let me repeat the process. Right, so now I have the Z, so I have Z1, Z1, and N Z1, right? And over here I have N Z1, right? The N. Easy to get this wrong. N the N. Then over here I'm just gonna get the Z bar. So notice here I'm getting in this block over here, I'm just getting the Z's. Here it's a mixed thing, right? And so over here, maybe I'll write this in a slightly, I won't write down everything, but here I have the Z1 bar, the Z1 bar, the second derivative over here. It's I'm not gonna write the other ones, but it's basically I'm just taking the bar of this, right? And over here, again, this is gonna be the bar of that. So I'm just really swapping which ones are the bars and which ones are the non-bars. So I'm gonna have so let's just write down the first one. And then the rest, right? And this matrix allocated to B, right? I'm saying it's the Hessian, but the real Hessian at B. Right? Again, you've seen the real Hessian is supposed to be in the x's and the y's. It's not this matrix. This is a matrix after a change of variables, right? But it is where there's various ways of writing this depending on if you're how you're writing change of variables, what you're trying to preserve. If we're thinking of the standard Hermitian unit product, then to make it so that this is this is still a nice real valued matrix. But we're doing the change of variables so that it's still we start with a symmetric, right? Because we have dx dy derivative is the same as dy dx, right? We started with a symmetric matrix. So this one is to make it Hermitian. That's why we're starting with the bars, right? On the rows and starting with the z's on here because we're applying a Hermitian in a product. So one side is bars, right? So that's the reason for writing it this way. You can write it the other way, but it doesn't really really matter. Now, with this, because it's again just a change of variables, right? It's this Hermitian matrix. It's a positive semi-definite if and only if the actual real Hessian in the original variables is positive semi-definite. That's all that it's saying is that if I'm applying the inner product, it's positive, and I did the change of variables to preserve that inner product, right? So here I will have that. Well, maybe it's maybe wrong to say that N is convex. It's really the set U, which is where R is negative. The reason why we're taking negative is that that makes if I take the derivative of R, it points out. So you have the outside normal, outgoing normal. And you could take the other way, but then you have to change signs and everything, right? It's just a convention. But if I want positive definite, then I have to take negative here. So we're taking where R is negative. So U is here, M is here. So M is the boundary of U, right? I mean, at some point P, and so they'll say U is convex. This is the definition. Convex at P. If X P or the Hessian, so I'm applying the standard inner product here. P, positive semi-definite for all, not for all X, but for all X P in the tangent space. So I guess just use the complexified tangent space because we're complexifying. Well, we have to actually complexified tangent space. Okay. Right. It's basically the same definition. If you're doing it in Rn, you're not complexifying anything. It's the same definition. You just use the actual Hessian that you had from calculus and the standard tangent spaces, right? So that's local convexity, right? Convexity for a smooth manifold. And just we were talking about yesterday about the differences between the global and the local. Okay, so this is the local definition, of course. It's easy to go from the classical convexity to this. If I have a U that has nice smooth boundaries, easy to say, easy to show that it's convex in this sense. But if I get this local, it's hard to show that the thing is convex. And it's so hard that it's actually not true. Because you might like, if you had a union of two balls, right? They're both locally convex, right? But they're not the convex set, right? But once you have, at least if you have connected set, okay, then the connected U, right? So you have a domain with smooth boundary, then this local thing, will give you the classical convexity as well, right? Okay, and as we said, classical convexity is not the right thing, not the thing that we want. Because classical convexity is not preserved under bihomorphic change of coordinates. So, and we'll do that computation. But there's a part of this, and there's a reason for writing it this way. This is the key to all of CR geometry. It's looking at this matrix and what happens in this matrix, right? Or at least part of this matrix, because parts of this matrix are irrelevant. Really either half or a quarter of this matrix, depending on how you think about it, that's relevant, and the other half is completely irrelevant. So if I write this H, and I'm going to write it, I'm going to basically, give these guys names. Again, they're not standard names. So let me make sure that we give them the same names I gave here. Okay, so I'm going to call this L. I'm going to call this Z. Then this guy, or maybe I'm going to call this Z. This is just this is a capital Z. That's the one that I'm not really interested in, right? So matrix is evaluated at P, so I'm going to put P here. This guy is again just a bar of that, so like this, right? So there's really two parts, right? Because the other things are just bars, right? There's the L and the Z, right? And this is the holomorphic Hessian, right? And this is called the complex Hessian. L and Z is the complex Hessian. And it's maybe slightly confusing notations. You don't want to think of this as the complex Hessian. That's the Hessian as far as holomorphic functions are concerned. If you have no real objects whatsoever, you're looking at this matrix. If you're looking at what happens with real objects under biomorphic change of coordinates, you're looking at this matrix. And just like for in the real case, if I ignore any structure on X, I can always flatten everything. So I can get rid of all the second derivatives. By biomorphic change of coordinates, I can get rid of these guys. I cannot get rid of these guys. Right? And that's basically just like if I have a complex manifold, by biomorphic change of coordinates, I can flatten it, right? Because I'm just interested in this, and that one I can change. That one I can change with with biomorphic change of coordinates. I cannot change this one. So let's look at what happens if I apply, because so first you look at what happens if I do linear change of coordinates, right? So if I have A. It's useful to think, well, what does that have to do with this thing? So the problem is this is an n by n matrix. This is a 2n by 2n matrix. But it already doesn't make sense, right? But that's because we're dealing with Z's and Z bars. So if I want this thing to act into Z's and Z bars, I'm really thinking of this as acting, taking Z and Z bar. It's going into A, Z, and A bar, right? That's the way I want to think of A as acting on the Z's and the Z bars, right? If I'm complexifying everything, if I'm thinking of Z's and Z bars, I want to think of this, right? This one, right? And now that makes sense. So what is this as a matrix? As a matrix, this is just A, 0, 0, A bar. So if I see how does this change under this this matrix, right? So really what I'm doing is taking the star of this and then doing this matrix in there. And then this matrix again. Right? That's the way that we do change the variables, right? If I apply a linear map. And so you look at this, compute it, and make sure that the bar is in the right direction. So I'm not going to do the computation, I'm just going to write it down. What is it about? So what you get out of this is equal to. So I look at so I look at this. That's great. That's great. The Hermitian LP. This is the Hermitian matrix. See it. If I bar this, I get this, right? L is a nice Hermitian matrix. This is the way I want to transform Hermitian matrices. Transform exactly the right way. This thing also essentially transforms the right way because this is not a Hermitian matrix. This is a symmetric matrix, just like this. It's just everything is barred. So over here, I'll have this thing. This is barred. That's good. And over here, I'll have that thing not unbarred. Over here, I'll have this thing. Of course, now everything is barred. Right? Well, or I can think of it as let's go back. Right. So that's the way that's the way this transforms. So you can really ignore this size. Doesn't really matter. It's these guys that are important, right? So this transforms the way it should. Transforms as a symmetric matrix. It is a symmetric matrix. Transforms the right way. This guy transforms as a Hermitian matrix. This is a Hermitian matrix. Transforms the right way. Right. Now this guy, the holomorphic change of coordinates are gonna. It's basically you're doing the same sort of same calculus as normal calculus on here. So the trick is this guy, right? Because this guy mixes the Z bars and the Z's, right? And that's really the bit that that we're interested in.
LP bar there, A star LP,
This one,
yeah, last.
it works out that way, but
Identity.
Yeah. So we get so LP is Hermitian, right? So it should work out. So
There should be transpose in the initial.
oh, there should be right? Yeah, like it's not really important what happens there. It's just it's just whatever the bar does to it, right? Right. I'm missing that here. Right. But I had it, and then I looked up. Anyway, the important bit is here, right? Because those are just once you know these, right? So everything transforms the right way. Is basically the point. Under a linear map, but of course we're not just doing a linear map. We're just not applying just linear maps. We're applying. I'm not sure if we'll have time to do this computation, but we're applying quadratic maps, right? And so the quadratic maps, it turns out that they don't really do much over here, and it's really because if you think about it, you're never doing quadratic derivatives in the Z bars or quadratic derivatives in Z's, right? So it's kind of you're looking at just linear derivatives just in the Z's or Z bars, right? Here you're doing the quadratic stuff, right? So it turns out that we can change these by a quadratic. Like, if this wasn't just a linear, if it had quadratic terms, it would change this stuff even at the point. If at the point P, it wouldn't change this, right? So we'll do that computation, but I think we can do change the order a little bit here. So let's do this computation why it changes, and we'll see if the other computation we'll do later why the thing doesn't change. But it's just chain rule, but I think this is a very useful computation to. Maybe I'll leave this for the discussion section, so it's already up. We're gonna need that many. Yep.
Here, how can it be both transpose and conjugate? Like LP star is just LP, right?
LP star is LP, yes.
So if A was identity, we just
maybe for the discussion section to make sure like whatever the thing is. I think it should be transposed there. I think. But yeah, it's not the important piece. But it's something like that, right? So like if you work it out, you'll get something there. But it's it's this thing with with something to make sure that the bars happen correctly, right? Anyway, so all right. So I'm leaving this here. And the important bits are here, right? And that's when you don't have to sort of follow through what the bar does. So you don't have to. That'll be an exercise to check that, or check it to figure out what it is. But it's it's that with something applied. All right. So now, if I have some, let's call this neighborhood B, and this neighborhood B prime, and I'm going to have M here, and M is given by R equals 0, and I will have a biholomorphism F that goes from B to B prime, right? So, I want to see how this changes variables, and over here, of course, I want to take whatever manifold this is over here. This is going to be some other manifold, and this is the F inverse of M, right? And I want to see how does the Hessian change, complex Hessian change when we do this change of variables, right? All right. So we have this. Let's call the variables here theta and the variables here z. Just we have keep track of it, right? So we really have r theta theta bar over here, and what we're looking at over here for the inverse, right, is r of f of z clone, right? That's the thing that we want to look at. That's the defining function over here. And like that, you know, because this is a biholomorphic, this is some defining function. It doesn't really matter which one I take, right? Because of this. So let's look at what happens to the. Let's look at what happens over here, right? Under this change of, so under more complicated change of coordinates, not a linear one, but a more complicated one. R composed F. Let's look at this part. So it's just holomorphic derivative. So Cj, right? Evaluate it at some point. Let me avoid writing where I'm evaluating things because that's just going to make it more complicated. Because we have to do two derivatives, right? But it's just chain rule, and the chain rule, as I said, like the useful thing about writing a smooth function in the function of zeta bar is that it tells you how to apply the chain rule, right? It is exactly as if these were independent variables, right? So that's how we're applying the chain rule. So let's make it oh, this is terrible. I should make this KNL. I'm copying from my notes, and I should use the same letters as there are in my notes. Otherwise, I'm going to get this wrong. Right. So I have this. So this would be the K one, right? It's valid, and then so M 1 to N. I have the derivative of R with respect to zeta M, right? I'm going through the derivatives here, and then the F M, right? The mth coordinate here, differentiated with differentiated with respect to L, right? First. Then I have and it takes these guys, right? So I have right over here the R, the theta bar M, right? And then I'm going to have the conjugate. That's what's being plugged in here. The nth component plug into nth component of the bars, right? And the L, right? So it's this thing. Now, if F is holomorphic, the conjugate of F is anti-holomorphic. So just bar everything. If F differentiated with respect to Z bar is 0, then F bar differentiated with respect to Z is 0, right? So this thing goes away. So this term goes away. So I really just have this, right? This thing is gone, and now I have to differentiate it with respect to ZK. So now I have so I'm going to have two things, right? So I have n, I guess in my notice I made it new, right? So I will have first it is over here, right? So I have the new first, then the n, right? And then I just get this guy, and the right, and this guy that didn't get hit, right? So and he here. Then I get the make sure I'm right, yeah. And now I have the those are the zeta, zeta nu, so I have the bars. Zeta mu bar, zeta n. So now I have the bar. Maybe I should just be doing it instead of reading it maybe quicker. This thing goes to 0, so this guy's not there, right? Which one? This?
No.
No, this it's M.
Yeah, M by del Z.
Oh, it should be L. Yeah, sorry. Yeah. Otherwise, it would be nonsense. Right, yeah, I didn't copy it right. Okay, and then we still have to differentiate this, right? Because that's there from product rule. So anyway, so this is gone, right? You didn't have to even do it, right? But this thing is that's where the well actually this is the sort of the following term. This is the oh, this is what I'm sorry. I have n let me just write it down. Talk about it. Might be better. And now we get quadratic parts over here, right? Quadratic bits. Now we get the k derivative and all this L derivative. Okay. What is this thing? This thing is this guy. Oh, sorry. Not this guy. Should I add something else there? It's the, if I have an X, it's the, no, it is that way. It's been too long. 1.5 hour lectures are, yeah, it is this guy. That's what this is, right? If F was really a linear, right? That's what I'm getting over here. Those are just the different components of the matrix, right? And this is just writing it out what this means, right? That's applying the matrix, right? This is the problem term, right? Because now I have the quadratic bits of F are suddenly making a difference, right? So this didn't drop out. So this is something. Who cares what it is? But it's not 0, right? Because the R was not 0, right? So you can't have just because R is real. You can't have the zetas. The bar of this is if I know this, I know the entire derivative, right? Because again, the bars and the non-bars have to be symmetric. So this can't be 0. So that means I can make this thing whatever I want, right? Because if I'm just applying some linear by the right sort of, without touching this, I can change this, right? Just by adding whatever to the linear terms, right? And so I can make this thing to be whatever I want, right? And so what it says is that I can change this is really this part of the matrix, right? So now I have this thing plus something, and then plus something I can make whatever I want. And so this thing is basically like nothing gets preserved, absolutely nothing. I can make it 0, or I can make this whatever matrix you want by adding in some quadratic terms, right? So out of this guy is completely not preserved, and that's basically that's the analog of being able to, if I have a complex manifold, being able to straight, right? It's exactly that this thing can be changed to arbitrary whatever I want, right? So next time I'll write this down for the if I put a bar here, this term is going to be here, right? Because I'm going to get one of these is basically a bar term, right? And so this thing, the quadratic, it's because I get quadratic terms, but they're all zero, right? So this thing will still be this, right? So under a holomorphism, this is still this, right? Where this is the derivative. I guess this would be the zero is the star is the z bar derivative of f, right? Or the z derivative of f bar, right? So that's sorry. Oh yeah. Now we went over it. Sorry about that.
Here, R is a summation, right? So you can just think of it, and you can do a change of coordinates and think of it as X or something.
Well, I mean, basically, that's the way to,
Yeah, and then from there we can do what you were like.
Right. Yeah. But you have to basically, so essentially.